Okay, we seem to be live. Welcome to Supercharged Math, Probability, Week 3. I am here. I am enjoying myself already. The class hasn't really even started yet. I am wearing my Crusaders shirt, which I'm sure I've worn before for Supercharged lessons. That is a rugby team from the South Island of New Zealand. They're actually really good. And I have my beautiful assistant Mocha with me as usual, although I'm not really intending to make her do very much of the work in this week's lesson because I don't find her very helpful when it comes to probability. She has trouble calculating the chances of things. Something about being a dog. I could do a question, very quick review. What is the chance, what is the probability that Mocha is cute? It's certain, of course. What is the probability that she will get all of the questions right in today's homework? That would be impossible. Okay, so that is a little bit of a review. She's all excited because she knows I'm talking about her, but I'm going to start ignoring her because she is kind of distracting. Okay, what else is there to talk about? I talk about the weather, so I will. It's really nice out. It's a bit sunny and very warm, and it actually makes me glad that I'm in the basement because it's nice and cool down here. So, let's get into the math for this week. We are going to be talking about the concepts of independent and dependent events and probability. So this concept didn't have to be applied in all of our examples from the last 2 weeks because we kept on calculating the probability of single events. And if there's a single thing, you don't have to worry about whether it's dependent on something else or not. But a lot of probability calculations involve multiple events. Very commonly with questions we practice with, there are 2 events. I'm going to give some examples from real life or at least from sporting life. Like for instance in baseball, if we could calculate the probability that the batter is going to hit a home run in his at-bat, well that's just one event. But we could also ask, well, what is the probability that the batter will hit a home run in 2 at-bats in a row? Okay, the calculations might be pretty complicated, more complicated than what we're going to do today, but you have to start to consider, when you're asking a question like that, like if you like baseball, you might be wondering this sort of thing. If the batter hits a home run in his next at bat, is it as likely that he will get a home run in the at bat that he does after? The answer kind of depends, there's that word dependent. The answer kind of depends on whether we ask the question before the game starts or if we wait for him to hit a home run and then ask the question. Probability can get complicated and it just gets interesting as it gets more complicated. But we're not going to try to calculate probabilities of baseball at-bats right now because, let's face it, an awful lot of things can come together to determine whether the player can hit a home run. The pitcher could intentionally walk him and then there's no way he can get a home run and he doesn't know ahead of time whether that's going to happen, that sort of thing. So that's where some of the things like when we use our dice and our number cubes, our coin flips, our bags of treats that we reach into, our cards. That's why we like to use those when we calculate our probability because as we're learning. Because it doesn't get quite so complicated as that at-bat. Another example, for instance, in football, and here I am with sports again. Maybe I should have been saying rugby, but never mind, it's football that we're talking about. What are the chances that a player is going to get a touchdown? Well, you might be able to estimate that by saying, well, this player has had a touchdown in 7 of the last 8 games. So maybe we could say his probability of getting a touchdown in the next game is 7 out of 8. But then what about the question, a dependent or independent events? What about asking the 2-part question, the 2-step question? What is the probability that he will get a touchdown in his next game and then get a touchdown in the game after? We are able to do some calculations to figure that out. We're not going to do a probability question that complicated either. The whole baseball, football thing is just a little bit not really appropriate for a beginning probability lesson. So then we get back into our games and our toys. I'm going to start with my first example with the numbered cube. Except I'm not just using one numbered cube, and yes, I have managed to find some larger numbered cubes. And boy, are these ever large. They're soft and they're fun to play with, and I have a feeling once my grandchildren see them, I may have trouble finding them for the next probability lessons after, but I will cross that bridge when I come to it. Okay, So what are the chances of rolling a numbered cube and getting a 6, and then rolling the other numbered cube and getting a 3? Well, you could ask yourself, why does he need 2 numbered cubes for that? And the truth is, the way I asked that question, I don't. I could calculate this question with 1 numbered cube. What are the chances that I will get a 6? And then, if I roll it again, what are the chances that I'll get a 3? Okay, I'm actually going to calculate that. Where's my chalk? This is a little bit of a review. We have talked about the numbered cubes before. We know that there are 6 numbers on the cube, so the successful over total, this chair is in the way, let me move it. The successful over total is, the total is 6. There are 6 numbers that can happen. And the successful of getting a 6 when you roll it is, there's only one way that can happen. So we have a 1 out of 6 probability that we will get a 6. But this was a 2-part question. I'll write it here. 6, then I think the second one was a 3. So what is the probability of getting a 6 and a 3? We have done the 6 part. The 1 out of 6 is the probability of rolling a 6. But then what we do is we find the probability of getting a 3, which is also going to be 1 out of 6. There is still only 1 3 on this. There are still 6 numbers that can happen. But when we calculate this, we multiply. So to know what the probability of is of getting a 6, sure, you only need 1 fraction. To know the probability of a 3, you only need 1 fraction. But to know the probability of getting a 6 and then getting a 3, you have to use 2 fractions and you multiply, and that gives you the answer. And that's cool, because we know how to multiply fractions, don't we? Numerator times numerator, we have 1. Denominator times denominator, we have 36. The answer is 1 out of 36. There is a 1 out of 36 probability of rolling a 6 and then rolling again and getting a 3. Only 1 out of 36 times. Well, when you think about it, all the things that can happen, you could get a 6 followed by a 1, a 6 followed by a 2. There's a lot of ways of getting 2 numbers that start with 6 as the first number, but then what about getting 5 as the first number, 4 as the first number? When you think about it, if you really list them, you will see that there are 36 different things that can happen. So that's one question. That's a starting question. I don't think I have to erase yet. I have a bit of space here. Next question is also using the numbered cube. It's only slightly different. Rolling a 4 and then rolling another 4. Well, and you know, here I am standing holding the cube. I haven't actually rolled it, have I? That's going to be a theme in today's lesson. Whereas I was actually doing things like pulling cards and rolling numbered cubes and flipping coins in the previous 2 lessons, in this lesson we're going to do an awful lot of our calculations to answer the questions. We're going to answer the question with calculations, which means we are using theoretical probability. We're not going to be doing experimental probability, and we're not going to be doing simulations. But I still like to have the numbered cube in my hand when I talk about it, because it makes us think about what we're doing with some concrete, colorful objects. And let's face it, I like the objects. They're fun to have. Okay, so the 4 followed by a 4. Well, I don't think you're going to be too surprised to see that the chances of getting a 4 with the first roll are 1 out of 6. It is a numbered cube after all, so it doesn't tend to change. And then we are multiplying that by the chances of getting a 4 the second time, and that's also 1 out of 6. So we're getting the same answer. 6 followed by 3 was 1 out of 36. 4 followed by 4 is also 1 out of 36. You might think, wait, 4 followed by 4 sounds less likely to happen. But it isn't less likely to happen, and our calculation shows us that. How are we doing for time? Okay, I was a little slow at the beginning of the lesson, but I have a lot of examples. I think I have a total of 20 examples, and I really do want to fit all of them into this hour. So I think the time is going pretty good. I will stop for a moment to take a sip of my water and to encourage the students to take a sip of their water too if they need it. That helps. And to take a stretch if you need it. While I'm erasing, I'm putting a new problem on. And I will also remind you that you can send me email, send me questions by email at doug@superchargedscience.com. And to remind you also that tomorrow is yet another week where we do not have a homework class tomorrow, but next week there will be one. And I may try to remember to remind you of this again later in the hour. Okay, so there's actually a cute dog standing right where I need to step, so I'm being careful. What's my next example? My next example involves the coin. So we're going to leave the number cubes behind for a bit. I'm going to take a brand new clean microfiber cloth and I am going to erase all of this, except for the title of the lesson, probability, title of the unit is probability, and the title of the first half of this lesson, which is independent. Why is it called independent? Why am I talking about that? There's a reason. And I will get into my third example, which is the one with the coin. Let's find my coin. And I don't have a giant coin to show you. Maybe I should try to find one of those. It would work a lot better with this camera thing because I can hardly even see the coin when I look in the video. We're going to talk about why I'm talking about the word independent. Okay, so the question though for flipping the coin example, again, we're going to do two events. We're going to flip the coin twice. Where we've left behind for now the type of probabilities where you just have one thing happening. We are having a two-step event. We are having two things happening. We're going to flip the coin twice and we're going to get a head, then another head. And the calculation isn't very complicated. In fact, it might seem a little easier than the ones for the dice, the number cubes, because the coin has only two things that can happen. So the chances of getting a head are 1 out of 2. And we are going to multiply that by the chances of getting a head the second time, which are also 1 out of 2. See, the thing about a coin is the head will stay on the coin. If I flip the coin and I get the head, I don't take the head away and put it in my pocket and keep it. The head stays on the coin. So that's why the chances of getting a head the second time are still 1 out of 2. And that is the meaning of the word independent probability. The chances of getting that head the second time are independent of what happened the first time, because the coin still has one head and one tails. That is the idea of independent. And then when we, when we use the number cube, I'll grab the green one this time. The coin is a very good example of independent probabilities, in events that are independent of each other in probability, and so is the number cube, because like the coin, if I roll that 4, I don't take the 4 off of the number cube and keep it. It's still on there, and the next time I roll it, the coin still has, the cube still has the 6 sides. It still has one each of 1, 2, 3, 4, 5, and 6. Nothing has changed, so the chance of getting that for the second roll are independent of what happened in the first roll. And that's really what you have to think of when you're trying to understand the meaning of independent and probability. So there are a lot of fun probabilities we can calculate with all sorts of toys and games and props that we like, that are where the two events are independent of each other, where what happens the first time does not affect what happens the second time. Okay, putting down that, I am going to, I guess I should finish this, eh? 1 over 2 times 1 over 2 is going to give us 1 over 4, or 25%. We don't always have to convert our probabilities from fraction into decimal and percent. The decimal, as I've said before, is not really all that useful. It's not as easy to express your answer in the form of a decimal. Fractions are very useful because when you're doing the calculation, you can really see what's going on with the fractions. We know there's one head, we know there are 2 sides to the coin. The fraction really shows us that. I like the fraction, especially for doing the work. And then to express the answer, you can say there's a 1/4 probability, but it might sound a little better if you say there's a 1 out of 4 probability. And that rolls off the tongue and has a meaning that regular people, including all those other people in the world who are not supercharged students who are studying probability right now, will understand. When you explain this to someone who hasn't been studying probability and you say there's a 1 in 4 chance of it happening, that means something to them. But there is a 25% chance of it happening also means something to them. So being able to express it as percentage comes in handy sometimes. And I will get back to that. Most of my answers, though, I'm just going to stick with the fraction. And then, of course, there's also the occasions where you will want to simplify the fraction. That's helpful as well. Okay, my next example. I only had one example with the coin. So I'm moving on to my next example, and we are going to use cards. Here are the cards. I'm not going to make a big deal out of opening this box and taking out the cards and pulling them, because yet again I am reminding you that what we're trying to learn to do here is do calculations. So it's enough to know what's going on with the cards. If you know that the deck of cards has 52 cards in it, if you know that half of them are black, half of them are red, if you know that there are 4 suits, the hearts, the diamonds, the spades, and the clubs, If you know that there are 13 different values for the card, if you want to use the word value, numbers, but they're not all numbers. So you have your king, your queen, your jack, your ace, and the ace could be a 1 if you want, and then you have the 2, 3, 4, 5, 6, 7, 8, 9. If you're familiar with cards, it's a little easier to do this. I have met students who were not familiar with this type of cards. And what I do is, in my classroom, I have a few decks of cards. What I do is I hand the deck of cards to the students and I ask them to play with it for a while. And the student, just by playing with the cards, just like anyone did, I can remember doing this when I was a kid, and I'm sure a lot of you have done this as well. Just by playing around with the card, you start to see the patterns, you start to memorize these numbers that come in so handy when you do your probability calculations. I'm going to put this down, and I'm going to put up my next example. So I'll erase my coin example. Let's see, I'm only on example 4. And, we have used 16 minutes, so I have to make sure I don't waste time. Example 4 is with cards. The next 2 examples are with cards. What I'm going to do is calculate the probability of, again, a 2-event probability, 2 steps. First, we are going to see what is the probability of getting a heart. Maybe I should have just drawn a heart. It would have been faster. But then we're going to put it back. Am I running out of room on my chalkboard? I better go down in line. We're going to pull a heart, put it back, and then get a 7. Why am I saying put it back? Because we are talking about independent events. The numbered cube, automatically, the second event is independent of the first one. It kind of makes it easy for that to happen. The coin flip, the coin is also automatically arranging for a situation where the second event is independent of what happened in the first event. But with cards, you have to be a little more careful. If you do a game where you pull a card and someone pulls a heart, if they keep the heart, well, you have changed how many cards are in the deck. And you've also changed how many hearts are in the deck. And we don't even know what heart it was, if it was a 2 of hearts or a 7 of hearts. You have changed the number of, if it's a 2 of hearts, you have changed the number of 2s that are in the deck. That wouldn't be independent. We'll get into that. We'll have some examples that work that way later in the lesson. But in order to make sure that the second event stays independent of the first event, we are going to put the card back. And I have to remember to say it. So if I forget, you'll find me saying, oh, oops, and I'll put it in. Even when I was preparing my notes for this, I kept on forgetting, and I kept on putting the little caret, the little thing, at the end, and saying, oh yeah, remember, put it back. Okay. So we have our scenario set up. It's a heart, we will put it back, and then a 7. Let me take a quick look at my results here. I never did the calculation. I forgot to do the calculation for that one, so I better get it right now. Okay, so how many hearts are in the deck of cards? There are 13 hearts. How many cards are in the deck of cards? There are 52. Uh-oh. We may have a problem. We are getting some rather large numerators and denominators now, which didn't happen with the coin flip, that's for sure, and didn't happen so badly with the numbered cubes. But with the deck of cards, you're going to see the number 52 quite often. But we won't worry about that yet. So the heart that we pulled has been put back. There was a 13 out of 52 chance of getting that heart. We are correct. But we are going to multiply that by the chance of getting a 7 with our second pull. Now, there are still 52 cards in the deck, because we put that heart back. What are the chances of the second pull getting a 7? There are not 13 7s in the deck, there are only 4. So we have this. Okay, I'm going to have to get my calculator. Yes, you know, I could show off and do all these calculations in my head, but just in case I were to get one wrong, I'm going to be careful. 13 times 4 I can do in my head. That is 52. Well, actually, if you think about how I knew there were 13 hearts and 4 7s, it sort of stands to reason that 13 times 4 is 52. So it might be a multiplication that a lot of students will have memorized. Even though 13 goes outside of the multiplication tables most people memorize, you can multiply the multiplication tables up to 20 times 20 if you want. You can memorize any multiplications you want. So 13 times 4 happens often enough, especially for those of us who either play cards or calculate probabilities, that's me. And we remember 13 times 4 is 52. But 52 times 52 is a calculation a lot of people are not going to want to do in their head. And I don't want to spend the time trying to do it right now. 2,704. Whew. But I can reduce this. I have a feeling that 52 is a factor of 2,704. Yes, I know it has to be because 13 times 4 is 52, and I have 52's down here. Well, I got 2,704 by multiplying 52 by 52. So when I reduce this, I'm going to divide by 52 over 52, and I'm going to get 1 over 52. So the chances of getting a heart, putting it back, and then getting a 7 end up being 1 out of 52. That's interesting, and it's fun. Is there another way that I could show this, though? Do we always want to deal with these big numbers? Not necessarily. So one thing that we can do is, as we're doing our calculation, when we get a fraction that can be reduced, we can reduce it. 13 out of 52 reduces to 1 over 4. And 4 out of 52 reduces to 1 out of 13. And when we do it this way, it becomes a little bit easier to do the multiplications. 1 times 1 is 1, 4 times 13 is 52. I feel confidence in this answer. It's the same answer I got this way. So when you're doing probability questions, when you set up the fractions in the pieces of your answer, if you can reduce the fractions, you can go ahead and do it. If the fractions are not too complicated, you may not want to bother until the end. But if they get getting complicated and that's going to stop you from being able to answer the question, then you may as well reduce the fractions right away, and so that you can focus on the probability, because that's what this lesson's about. Okay, that was only example 4, so I better get busy. I'm going to do example 5 right away. We are sticking with the cards for now. Let me find my, the other examples are on the other side of the same piece of paper. So now we are doing the last card example I will be doing for now. But that was fun. I have to confess, if I were to keep on doing numbered cube examples, I might get bored after a while, because the numerators and denominators, not too many things can happen. And especially the coin flips, with the 1 out of 2 chances, doing that after a while can get a little bit boring. But cards don't tend to get boring, because the variety you can have in those numerators and denominators keeps things fresh. Okay, so my 5th example. Pull a 2 or an 8, put back, remember we're doing independent, so in order to make sure that it stays independent, I have to put the card back. So we're pulling a 2 or an 8, put it back, and then a red. Okay, so let's do this. We're going to do it the same way we did the last one. 2 or 8 is slightly different. We know the denominator is 52. How many 2's are there? How many 8's? There are 4 2's and 4 8's. So it's an 8 out of 52 chance of getting a 2 or an 8 when you pull that first card. But then we have to multiply that by the chance of getting red from the second card. There are 26 red cards in the deck out of 52, and we're getting those large numbers again. So I want to reduce. If I divide 8 and 52, both of them by 4, I get 2 out of 9. Is that 9? Did I get that right? No. Sorry, I'm going to erase that. Why did I get a 9? 52 divided by 4 is 13. And then 26 out of 52, that's an easy one. 26 is 1/2 of 52, so this reduces to 1/2. Now we have numerators and denominators that are a little easier to handle. We multiply. 2 times 1 is 2. 13 times 2 is 26. Our answer could still be reduced a little bit, because we could have done some canceling, but it's not a fractions unit that we're doing. So we're dividing by 2 over 2, and we have 1 over 13. There is a 1 out of 13 chance of getting a 2 or an 8, and then a red if you put the card back to make sure that it stays independent. That's it for that example. Even though it seems like a complicated example, it doesn't take that long to do. The first card one you might talk about a little bit more, and you might have to look and think a little bit more. But then that's one of the fun things about doing these examples, is that you can do so many questions and you can practice, and a lot of these steps start to become very fast and easy to do. I hope the students agree with me. Still have this in my hand, so I'm going to erase and look at my next example, which is a little bit different. And I think is kind of fun. Now, I made a cloth bag. It's made out of this orange cloth. I did not do the best job of making it. I didn't have the sewing kit that I needed, and I ended up putting it together with a little stapler, and I didn't have enough staples. So I'm kind of holding the bottom right now so the stuff doesn't fall out. What's in the bag are some things I found in the dollar store. So this is an orange whistle. So any bag can be used. I like the idea of a nice cloth one. And any items you can be used to put in it, and you can create your own game of chance, and that is a lot of fun. Household items work. In this set that I bought in the dollar store, I just bought one package. I don't know if we can see the colors that well. I have a red and an orange here. The red and the orange are kind of close together in color, so not so easy to see, but I'm just going to tell you what we have. Okay, I'm going to list it on the wall. There are 2 red whistles. Make sure that the camera can see that. I have a lot of space over here I'm not using. 2 orange whistles. But there's only 1 green. And there's only 1 yellow. And whenever I do my questions with the whistles, I'm always going to have this assortment. So even if I erase this, I have memorized, because I've been playing with these for a while, that I have 2 red, 2 orange, 1 green, 1 yellow. I like that. I like that we don't have 2 of each or 1 of each. It makes the numerators and denominators a little bit more fun to work with. Makes you slow down and think a little bit. Now, the fact that my cloth bag isn't very good, and in fact things are trying to fall out the bottom of it right now, doesn't matter, because we are not doing experimental probability. I will be fixing up this bag and making it better though. Because we're going to answer our questions with the fractions and the multiplications. What was this particular pair of events? Because we are doing independent, so I wanted to have a 2-event probability. This time it's red followed by green. So I'm writing red, and I'm writing green, but I'm also remembering to say put back. Because the whistles, that's messy, but you'll forgive me. The whistles are kind of like the cards. I could pull that red whistle out of the bag, but if I keep it, I'm changing what's in the bag. I want to make sure that what happens the second time I pull an item out of the bag is independent of what happened the first time. So I am going to put the whistle back. Red, we know that there are 2 red and there are 6 whistles altogether. So we have a 2 out of 6 probability of getting a red. Green, there's only 1 green out of 6. So we have a 1 out of 6 probability of getting green. Because we put it back, the 6 stays a 6. And the question is, I guess, a little less complicated. When we multiply these, we get 2 over 36, which reduces to 1 out of 18. We have our answer. We are doing the same multiplication trick all the time, and it must be starting to feel easier and easier. I hope it does feel easier to the students, and I hope it feels fun. So the whistles in the bag thing is something, the thing I like about it is it's something you can do yourself. Now, I could have used a bag from a store. I could have used a big giant sandwich bag. I'm avoiding the transparent bags because when I pull the item out of the bag, I want it to be a surprise what I get. I don't want to be reaching in there saying, oh, I'm going to aim for that red whistle. I like the red one the best. So having a bag you cannot see through helps. But any sort of bag, and you can use a big sock. You can use all sorts of things. You can use a box. You can use any container that you can't see through very well that the items fit into. And then any items you want. So you can really make your own game and make your own probability questions as much as you like. So that was the first whistle example. I'm going to do a second whistle example. So I will erase this one. I'm leaving part of the word red there because I looked ahead and I saw my next example also starts with red. So I'm going to write probability of getting a red, and then remembering, put back to keep it independent, and then not orange. Is this fitting on the chalkboard wall? Yes, it is, quite well. Okay. Red, put back, not orange. So here's another fun thing you can do, even with a simple scenario like this where there are only 6 whistles. That makes you able to create a lot of different and interesting questions. You can use the concept of complementary. Not orange means all the ones that are not orange. It means red or yellow or green in this case. So the probability of getting a red is still 2 out of 6. Same as it was last time. Because we put back, the probability of not getting an orange, let's slow down and make sure we don't make a mistake. Well, there's still 6 whistles in the bag, so that part is faster. The ones that are not orange are the 2 reds plus the 1 yellow plus the 1 green, so there is a 4 out of 6 probability of getting not orange. And when we multiply, that gives us 8 out of 36, which is divided by 4, 2 out of 9. That's the 9 that I was trying to write before. I had that 9 in my head because I knew I had a 9 in one of my examples coming up, and that's it. Okay, so we have our answer, 2 out of 9. We can convert that into a percentage if we want, but we don't have to. Red, put it back, then not orange, chances are 2 out of 9. How am I doing for time? I think I'm doing better for time. I'm getting to the end of my examples for the independent events because that is the 7th example. We're starting to do quite well. Now we're going to do another game that I made, another cloth bag. This one's in even worse shape. The cloth isn't even attached all the way to the top because that's where I ran out of staples. The good thing about this bag is it doesn't have a hole in the middle because I made it by folding over a piece of cloth and I made sure the fold became the bottom. So that worked better. And what do I have in there? I have little dry erase markers. Now these ones are kind of close together in color, but they are different colors. This top one, I don't know if it's supposed to be purple or pink. I'll call it pink. And the other one is red. Altogether, I put 10 markers into the bag. I had a couple of extras and I put them aside because the packages of markers I bought resulted in me having 2 of each color. And I wanted to keep it a little more interesting than that. So I'm going to erase this, which means if we do the whistles again, we're going to have to remember what we had. But I know I do remember, so we should be okay. I'm going to, actually I'm not going to erase all of this because I do have 2 red markers. So I'm going to write, do I have room? Yes. Markers. Okay, that R is a little messy. Okay, I do have 2 red markers. I do have 2 orange markers. Do I have to make sure? Let me look. You can't see this very well, sorry. Yes, 2 red, 2 orange. I'm going to have to dump these out so I can remember what I have. 2 red, 2 orange. 2 purple, 2 green. So I will change this green. Do I have yellow? No, there's no yellow in there. There were no yellow dry erase markers. Well, actually, yellow would not be the best color for a dry erase marker, would it? So 2 red, 2 orange, 2 green, 2, I wrote purple, but I'm going to call it pink. I think pink is a better description of what I had. And then there are 2 colors I only have 1 of, which is 1 blue and 1 black. Here's the teacher in me coming out. I just can't help but say it. You've heard me talk about how white is the best color for the chalk, while black is the best color for the dry erase board. Okay, now I dumped them out so I could see them. But the thing is, I don't really have to put them in the bag because I'm not going to use pulling out of the bag because I'm not doing experimental probability. I'm going to erase this though, this whistle problem. The first example with the markers is a blue, put it back, and then a black. So I'm going to do that. Blue, put it back, then a black. No, I'm going to change it. I'm going to say pink. Pink, put back, then black. Okay, because there are 2 pink. How many do we have altogether? It's a very quick little addition problem to realize that we have 10 markers altogether. 2 of them are pink. Because we put back, afterwards when we do our second pull, we will have 10 markers again, but there's only 1 black, so this is going to be a 1. It's the same math, the math hasn't changed, which is why I would expect the students to think, okay, well, this isn't any harder. There's more markers, there's more colors, but the math isn't, there is not more to the math, not really. We keep on multiplying the two fractions. Because there are two events in our independent events questions, we keep on multiplying two fractions. And that becomes easy if we practice it a little bit. 2 times 1 is 2, 10 times 10 is 100. We have a fairly large denominator. If we reduce this, we will get 1 out of 50. 2 over 100, I'll remind you, can very quickly be turned into a percentage, of course, which means it's 2%. 1 out of 50, or 2%, is the probability of getting a pink marker, then getting a black marker, so long as you put the pink marker back. So that's the first marker example. Now the next one, oh, these are getting really exciting now. The next one is a mixture of markers and whistles. So I'm going to leave the information about the markers here. And I'm not going to write the information about the whistles again, because I think we remember it. But what are the chances of a yellow whistle? So I have to write whistle, even though there were no yellow markers. I'm going to be clear about what I'm talking about. A yellow whistle, and then, put a comma. What was the other one? A green marker. And something that I find interesting has just happened, which is I didn't have to write put back. Why wouldn't I write put back in this situation? Because we know that whether or not we get a green marker has to be independent of what we got from the whistle bag. It's 2 different bags full of 2 different collections of stuff. So I found another way to make things independent in a probability question. If you do a coin followed by a coin, it's independent. If you do a number cube followed by a number cube, it's independent. If you do markers followed by markers, you have to say whether or not you're putting it back. And in all the independent questions, you will be putting it back. But when we switch from from whistles to markers, that's going to be independent for sure. And I don't have to say put it back. Okay, so a yellow whistle, remember, there were 6 whistles, and there was only 1 yellow one. And we're multiplying that by the probability of a green marker. There are 2 green markers, and there are 10 markers altogether. So we have 2 over 60, which reduces to 1 over 30. That will also turn into a percentage, but it's going to be a percentage with a decimal in it. I'm not going to bother doing it right now. The important thing about this example is the emphasis on the idea that we do not have to say we're putting the whistle back. We don't have to put the whistle back because we're not using the bag of whistles again in the second half of our probability. That's interesting. And again, it illustrates how much variety there is for you to do this when you're practicing. When you take your household items and put them in a bag or a box, there is so many different things you can do to keep this interesting. Okay, my last example from the independent events also is a mixture of markers and whistles. I'm going to erase, where is my microfiber cloth? And I'm also going to take a sip of my can of water because I am starting to get that chalk in the throat feeling of talking too much and being around chalk dust. I don't really think I'm getting chalk dust in my mouth very much, but it kind of feels that way. My mouth is dry because I'm talking like crazy. Okay, so this last example for independent, because the lesson's not over yet, is a marker that's not blue. That'll take a little bit more space to write. I didn't write the H very well. Marker that's not blue. Then, where'd it go? A whistle that's not red. So again, because I'm switching from markers to whistles, I don't have to say that I'm putting something back. I have to make this chalk longer. Okay, So we are going to do, it's two events, so we're going to have two fractions, we're going to multiply them, that keeps happening. There's Doug illustrating his other point he always makes to the students, which is it's good to put that skeleton down onto your page when you're starting to do a calculation. When you know you're going to multiply two fractions, before you worry about what the numbers are, you can put the two fraction lines in the multiplication symbol, and it gives you, instead of blank space on your page, it gives you something to start with. Okay, so the first thing was, oops, I wrote marker. Marker. That's not blue. Okay, well, there are 10 markers. And all of them are not blue except for that one blue one. So 9 of them are not blue. And then we're doing a whistle that's not red. If you'll remember, there were 6 whistles. And there are 4 whistles that are not red. The 2 orange, the 1 yellow, and the 1 green. So we're going to get our answer with these fractions. Now I could do some canceling, but the numbers are not too huge. 9 times 4 is 36. 10 times 6 is 60. We have a 36 out of 60 probability of getting a marker that's not blue followed by a whistle that's not red, and we don't have to talk about whether we're putting something back. I can still reduce this though. 12. I am going to divide top and bottom by 12, and I get 3 over 5. Oh, a 3 out of 5 probability, and then my percentage brain says, oh, that's going to be 60%. There's that percentage coming up again. Okay, but that's interesting. It's 60%. Am I surprised? Do I think that this should have given me a bigger percentage than 60? I'll point out something about this. I think this is an interesting thing to look at when you're playing with numbers. 9 out of 10 is 90%. That's actually a pretty easy one to convert. 4 out of 6 reduces to 2/3, and I happen to know that that is 67% if we do a little bit of rounding. This is really big. 90% is very large. I mean, the biggest it could be is 100. 67 is also really big. And this one is 60%. It's interesting. Why would you multiply a very large percentage by another very large percentage and get a percentage that's smaller than either of them? Does that sound like what you would expect to happen? It's interesting because percentages could trick us into thinking, wait, we must have done something wrong. But when we look at the fractions, then we start feeling a little bit more confident that, no, this is okay. We have, the 9 is smaller than the 10, the 4 is smaller than the 6. So when we multiply them, we get a numerator that's smaller than the denominator. Something happens when you have values that are less than 1. 9/10 is less than 1. And it's easy to forget that 90% is also less than 1. Because, of course, the whole in percentage is 100. So a number that's less than 1 times a number that's less than 1 gives an even smaller answer. And that's just part of number sense. And that's part of the fun of math. And that's the only reason I'm mentioning it, because it's the sort of thing I would talk about mostly in a decimal and percent lesson, not in a probability lesson. So leaving that behind, I'm going to move on to my next examples. Let's take a look at the time. I think I'm going pretty good with time. The markers will come back, but the list of colors will not. I'm going to have to just look at that chair over there where I dumped them out if I have to remember how many of each there are, because I am erasing this. And I'm erasing this example. This is why it's so nice to videotape the lessons, because when I erase an example, if I thought it was a good example, I feel sad because I think, oh, that was so useful for learning from, and now it's gone, I got rid of it. Not really. We have the video, so we can look at that example forever if we wish. Okay, I am actually moving on to another page. I am having trouble reaching it because there is a dog on the floor there. Now we are going to move on to the next part of our lesson, and I have to change my heading a little bit because we are going to start talking about dependent events. We've already hinted at what we're doing, which is why I covered the independent for more than half of the hour. The dependent events work a lot the same way, but they're dependent. They're no longer independent. So we have to slow down and think about that. Okay, so my first example is with the whistles. I'll write the word whistle just as a reminder that that's what we're working with now. And our problem is green, then yellow. And I'm leaving that space again, but not to write the phrase put back. I'm writing the phrase keep it. So we're back to that idea of the card trick where the person says, pick a card, and the person picks a card, but then the magician will say, don't show it to me, put it in your pocket. So that means the person kept the card. That would not be an independent event. That would be dependent. That's what we mean by dependent. So understanding independent is easier if you know what dependent means, and vice versa. And learning both of them at once, the way we're doing in today's lesson, is useful. Because you understand one, as soon as you understand one, it helps you to understand the other. Okay, so we are pulling a green whistle, but we are keeping it. Someone put it in their pocket or something like that, and then it's a yellow whistle. So can we come up with a real life situation where this could happen? I can, easily. That bag of whistles that I bought in the dollar store was actually meant to be the sort of little toys you put into a swag bag, I think it's called, a treat bag for a kid's birthday party, for instance. So you don't want to have to, when there are a lot of kids coming to a party, you want to be able to buy a bag of things that you can spread out onto all these little bags. So the whistles, that's what they're designed for. So let's say it was a birthday party, and let's say I put a green whistle into one of the bags for one of the kids. Well, that's staying in the bag. The bag is keeping it. That kid is keeping it. So when I'm calculating the probability of getting a yellow whistle when I go to give a whistle away to the next kid, I'm not in an independent event anymore. I am in a dependent event. Whether we get a yellow whistle with the second pull from the bag depends on whether we got a green whistle or some other color the first time. So this is dependent, that's what happens. And of course something happens with the fractions as well, which I may as well start showing by putting my skeleton. Okay, the chances of getting a green whistle were 1 out of 6. Reminder, there were 6 whistles and only one of them was green. But we keep it. So the chances of getting a yellow whistle are not going to be 1 out of 6. They were before, but now that one of the whistles is gone from the bag, we don't have 6 whistles anymore. That denominator finally changed. And this is how the denominator changes. It changes because these events are dependent. When that happens, when you're doing dependent events where you kept the card or you kept the whistle, the denominator will change, and it will tend to always change the same way by going down by 1. So it's a pretty easy change to keep track of. Then, how many yellow were in the bag? There was only 1 yellow whistle in the bag, and it's still there because the first one we pulled was green. So we have a 1 as the numerator. So our answer is a little different. Our problem has changed slightly, but not very much. 1 times 1 is 1, 6 times 5 is 30. We have our answer. The chances of the green whistle followed by the yellow whistle are 1 out of 30 if the green whistle was kept and not put back. Okay, so that isn't actually very hard. And all the dependent events are not very hard because they're very similar to the independent events. We just have to slow down and think about this idea of something being kept, not put back. Okay, so my second one's a bit of a challenger question though. I won't give too many challenger questions, but I just couldn't resist this one. I don't have to erase everything. I'm going to erase just this. That way I don't have to do as much writing with the chalk. So I did mess up my P in the word keep. Okay, so a green whistle, we're going to keep it, and then we're going to get a green whistle. I told you this is a bit of a challenger. We have to watch out. So the chances of the green whistle were 1 out of 6. There was 1 green, there are 6 whistles. We kept the whistle, so the amount of whistles has gone down to 5. But then getting the green, we took the only green whistle and kept it. So there are 0 green whistles left in the bag. That is a little bit of a trick question, if you will, because you don't get zeros in these calculations very often, but you can. Of course, I don't want to be afraid of that. I want to be able to handle it. When I multiply my fractions, 1 times 0 is 0, 6 times 5 is 30. I have a 0 out of 30 chance. That reduces, if you will, to 0. What does this mean? It means something that we talked about in the very first week of probability. It means that it is impossible to get 2 green whistles from a cloth bag that only had 1 green whistle in it. Remember certain, likely, and impossible? Well, this is an impossible. And this is what happens to the math when you have an impossible situation. Nothing to be afraid of. We know how to handle 0 when we're doing math calculations. I like that question, but I'm not going to do it again. That's the only one like that, the only impossible situation I'm giving in today's hour-long lesson. Okay, so the next one. And this is going pretty quickly. I'm not really suffering too much for time. How about, and we're still with whistles, red, keep, not red. I have to erase all of this. We're going to try a red whistle. I will remind us that we will keep it. And then the second one will be not red. So we're trying that complementary thing again. When you see the word not, you're applying the concept of complementary. A red whistle. There were 2 red whistles, so the probability was 2 out of 6 of getting a red whistle. But we're keeping it. So when we pull the second whistle, we now only have 5 whistles. That goes down by 1. How many of those are not red? The one we kept is red. So how many in the bag were not red? They're all still in the bag. There are the 2 oranges, the green, and the yellow. There are 4 of them. We can do this. 2 times 4 is 8. 6 times 5 is 30. I can reduce this to 4 over 15 if I want. I can convert it to a percentage if I want. Red, keep it not red with whistles is a 4 out of 15 probability. It's not taking very long to do a new example because we're getting good at this. Okay, next example, I am switching, where is my page? I'm looking at the wrong page. I'm switching back to the markers because I don't want to only do the whistles. It gets too easy if you always keep sticking to the same game. So that means I will erase this word whistle and I will put the word markers in its place. Or maybe I'll just write marker. Whistle, marker. Doesn't have to be plural, I guess. Okay. Markers. We are going to do, not red or black, then keep, and then red. Okay. Not red or black. Running out of space. Keep. I won't write keep it, I just write keep. And then red. Okay, I'm doing my best to become confusing, aren't I? Not red or black here, but then for the second I want it red. Really, so long as I am organized in how I write down the information, it's not really that bad. Okay, so it's the markers. Remember there were 10 markers in the bag. How many of them were not red or black? There was 1 black and 2 red. Altogether there are 3 markers that are red or black. There are 10 in the bag, so that means applying the concept of complementary. There are 7 markers that are not red or black. Not so bad. Now, we're keeping it, so the number of markers has gone down to 9. Come on. 6 down to 5, 10 down to 9. It's really not that difficult to do. It has a tendency to work that way all the time. That kind of makes it easier. Okay, red. I took out 1, but it was not red or black. So the number of reds has not changed in the bag. I started with 2 red markers in the bag. There are still 2 red markers in the bag. I'm able to complete my calculation. 7 times 2 is 14. 10 times 9 is 90. This reduces, if we want, to 7 over 45. And we can convert it into a decimal or a fraction if we, or a percentage if we want. That's it for that one. So it was markers. The numbers are bigger, but the example still went by really quickly because we are getting good at this. Okay, now, next example. Orange, keep, and orange. I made a mistake when I did it the first time on the paper. So I'm going to keep that question because there's nothing wrong with it. But when I answered it on my notes, I was doing whistles. I'd forgotten that we had switched over to markers. We're going to stay with the markers. So I'm going to do orange, keep orange with markers. Okay, let's erase. I have to erase all of this. I could keep the word keep, but I'm not going to push it that far to try and save writing on the chalkboard. Orange. Keep it. So all of our examples have been dependent since we switched over. In the second half of the lesson, we switched to dependent. So we keep on knowing keep it, keep it, keep it, keep it. The first half of the lesson, we kept on put it back, put it back, put it back. We can handle both. And I'm pretty confident that the students can handle both. Orange, keep orange. That was it, right? Okay, orange, keep orange. It's markers. There are 10 of them. 2 of them were orange. Were 2 orange? Yes, there were 2 that were orange. But we're keeping one, so now there are only 9 markers, and I took one of the orange ones and kept it. So there's only 1 orange left. So I've basically, with the last 2 examples, shown both of the things that can happen in a way with this numerator. You have to check whether the first event, whether you kept that color. And if you did, well, that's also going down by 1. Interesting, look, the 10 went down by 1, but the 2 also went down by 1. 2 times 1 is 2, 10 times 9 is 90, that is 1 over 45. If I want to reduce the fraction, I have my answer. The answers are coming thick and fast. Okay, another one with markers. This time I didn't actually make up an example. So, I think just for fun, because I think the students can handle it, I'm going to do a 3 event. Now, mostly we're sticking with 2. But I'm going to do a 3 just to say, well, you know, you can do more than 2 events in your multiple step probability calculation. So let's make up a marker event that has 3 things happen. How about, blue, keep it, then not green, blue, then not green, and then green? Should I do a green? I have to write keep again though. It's a good thing this chalkboard wall is so long. Keep, and then I'm going to do green. Let's see if I have managed to put together a multiple step event that is logical. So we'll test it. And if I don't like it, I'll just erase it and change it. Okay, so the first thing is there are 10 markers. And how many of them are blue? There's only 1 blue one. So that was fast. Now we're multiplying it by the second one. The number of markers. We kept the markers, so there are now 9. How many of them are not green? Well, the blue one's gone. There's 2 green ones there. Complementary says 9 markers minus the 2 green ones that are still in there means 7 of the remaining ones are not green. So far this is working. But now, the number has gone down by 1 again because we kept again. And now, we got not green, so both greens are still in there. So 2 of the 8 remaining markers, this worked. I actually managed to put together an example that worked, improvising without having pre-planned it. That was a risk. Okay, 1 times 7 times 2 is giving me 14. We know how to multiply fractions. When you want to multiply 3 fractions, you can. You just can multiply them all at once, or you can multiply the first 2, get an answer, and multiply by the third. You actually get to choose how you do that. 1 times 7 times 2 is 14. This is a little bit bigger though. I'll do the 9 times 8 first. 9 times 8 is 72, and then multiplying by 10 is easy. 72 times 10 is 720. I will leave it up to the students to reduce that fraction because I want to fit a couple more examples in. Let's see here. I don't have very much time, but I am allowed to go over my hour if I want. So if I go over by a couple of minutes, that's fine. I think that happens most weeks anyway. All right, my next one is to mention dice. And I haven't really written anything on the chalkboard because this is more of a thought. Okay, we are still in the dependent part of this lesson, and I'm asking myself, can I do a dice problem that's dependent? And that's tricky because with the dice, I mean the numbered cubes. The numbered cubes, how do you keep it? So I'm just going to say how I would do it if I really wanted to. I could say roll a 4, keep it, and then roll a 3. How about that? 4, keep, and then 3. Okay, the 4 that's the easy part, the first event. There are 6 faces on the number cube, only one of them is 4. But how are we going to keep the 4? The only way I can think of is to get a marker, a black marker or something, and cover up the 4 so it's there, and I have to remind myself, okay, it doesn't count, there's no 4 on the number cube anymore, and then I would be able to subtract by. It is possible, but I would kind of ruin my number cube if I did that. And then of the 5 numbers that were still on the cube, one of them is a 3. I'm still able to answer the question. It's just a little awkward. When I want to do a dependent question, it's better to just avoid the number q. And I'll say the same thing about the coin. I'll leave the students to answer this as well. We could do a question where we somehow keep the heads or the tails that we get with the coin. Again, you're going to have to cover it with tape or put marker over it and remind everyone, okay, this coin only has one side now, or it's not working very well. In fact, even this idea of putting black marker over this is a problem because, you know what, it's really not working. So when you're deciding, when you're making probability problems to practice with, be careful of this. Because I thought I was coming up with a solution to this problem, and then I just realized now, no, I didn't come up with a solution. I'm not even going to talk about the coin. When I put the black marker over the 4, I may have made it so that there's no 4 on the cube anymore. That's fine. But the problem is that face is still there. It's not going to be easy for me to remove the face so that there's only 5 faces this can land on. That becomes too awkward. It's not worth it. So now I move on to my last pair of examples, which are back to the cards. Okay, I'm going to erase. And I'm doing 2 examples because what I want to do is do a card example that's dependent and then do the same example independent. Or I don't know which one I'll do first. Okay, so cards. I'll write cards to remind us what it is we're dealing with right now. Okay, how about the queen? Then we keep it, and we know we can do that with cards. That works well with cards. It doesn't work with the coins or the numbered cubes. And then a 3. Is that what I had? Yes, it is. So queen, keep, then 3. Well, how many cards are there in the deck? There are 52. How many of them are queens? That's 4. I can reduce this right away if I want. That's a 1 out of 13, 1 over 13 fraction. I'm keeping it, so pulling the 3, there are now only 51 cards. And how many of them are 3s? 4 of them are 3s because the one that I kept wasn't a 3, it was a queen. And this I can't reduce. So I'm just going to multiply by 4 over 51. And it is giving me an awkward looking answer. 1 times 4 is 4. 13 times 51 is, where's my calculator? 13 times 51 on 1, 3 times 5, 1 equals 663. So remember what I said about getting a lot of interesting variety with your numerators and denominators when you work with cards instead of number cubes or coins. Well, that sure happened here. So if you pull a queen and keep it and then pull a 3, the probability of that happening is only 4 out of 663, and we're able to calculate it. But now, let me see here, where am I going to do this? I don't want to erase. Might need the calculator again. Okay. I'm going to do the same question. So what I'll do is I'll just make a space. I'm going to do the same question, but it's going to be the same, the queen, but I'm going to put it back. Then a 3. So this question I can do dependent or independent, depending on what I feel like doing. And the 4 out of 52 is going to be the same. The chance of getting that queen from the first pull from the deck of cards is going to be 4 out of 52. But now I put it back so the number of cards stays at 52, or back to the type of example we did at the beginning. And how many 3s are there? There are 4 of them. Both of these reduce to 1 over 13. So I actually have small enough numbers so that I can do the numerator in my head, and maybe if I'm a bit of a show-off, I can do the denominator in my head as well. And maybe if I'm afraid to be a show-off, I can also get my calculator and do 13 times 13. And yeah, I got it right. Okay, maybe I would have been better off just not saying that part out loud. But I am the probability teacher who does say the quiet part out loud, and I am reaching the end of my lesson. I've gone over my time slot, but just by a little bit. I will give my usual goodbye message. I will remind you that you can send me questions at doug@superchargedscience.com. I will remind you that there is no homework help tomorrow, but there will be one next week. And I will say goodbye from me and my beautiful, but this time rather useless assistant Mocha. I'm looking forward to next week, and I will see you then.